Natural resources, particularly the non-renewable ones, are geographically concentrated and may have specific implications on the socioeconomic outcomes of the individuals living in regions abundant in such resources. Coal is an essential source of energy worldwide, feeding into several other industries and activities, making it no less valuable than gold, thus black gold. It is a strategic resource for India as well. Hello, I'm Himani Pandey, a PhD candidate at the Department of Economics, and I am looking at the effect of coal mining on children's education in India. Coal mining activity in India is concentrated in central and eastern parts of the country. This provides us a natural setting to explore the trade-offs that families living in these regions face versus other regions of the country in terms of the schooling decisions they make for their children. Local economy in these mining regions presents the individuals and families with differing conditions in terms of labor market opportunities, environmental factors, and infrastructural setups. These could impact the schooling outcomes for children living in these regions who constantly are divided between going to school or going to work as child laborers. The objective in my research is to explore how the probability of a child living in coal districts of India to attend school is affected when exposed to the rising international coal prices. Using international coal price movements allows us to avoid any dependence on local factors or policies that may have an impact on education of children in a region. These prices are completely independent of local policies and institutions in India, but they significantly impact the local coal prices in India and are therefore an appropriate variable to compare the effect of coal mining activity in India on the education of children living in these regions versus regions with no active coal mines. The data from India suggests that between 1999 to 2011, the proportion of children attending school has increased from 69% to 89%, whereas the proportion of children working has declined from 28% to 9% respectively. A difference in difference analysis allows us to explore whether this increase in schooling proportion can be attributed to the presence of mining activity in a region and by what magnitude. The results suggest that mining activity in a region indeed generates favorable outcomes for children in these regions by positively affecting the probability to attend school. When international coal prices double, the probability for a child to attend school in these regions increases significantly compared to children in regions with no coal mines by 4 to 5 percentage points. These positive outcomes can be understood through the interplay of the opposing positive income effects and negative substitution effects. Income effects are the positive effects in household spending when there's an increase in the real income in the economy. In this case, the positive pull in the local incomes comes due to the rising coal prices, which increases the economic activity in the mining region, generating more jobs and more incomes. The analysis suggests that families which have middle-level wealth witness significantly increased probability of school attendance for children, but very poor families are not able to benefit from the rising family incomes as much because they use it to meet the essential needs and still prefer the children to work for family income. Very rich families, on the other hand, are unaffected by these trade-offs as their children do not need to work for the additional family income at all. Substitution effects are the implied costs that one incurs on losing an opportunity, which in this case of schooling is the opportunity to work. Results suggest that when faced with increasing international coal prices, the households in coal districts of India do not prefer to send their children to work for additional income. This negatively affects the opportunity cost of education, thereby weakening the substitution effects. Given that the international coal prices significantly impact the domestic coal prices in India, they alter the local labor market conditions in these regional economies. Increased demand results in rising income levels in coal mining regions, and with limited impact of substitution effects, middle wealth families benefit immensely when exposed to the coal price rise internationally. These families can overcome the cost of education, direct and indirect, thus deciding to send their children to school. Therefore, natural resources, when sustainably mined, can generate positive outcomes at a local level and benefit the local economy and its people in various ways. This is important for developing nations where the abundant natural resources can be a source of growth and development for the local people. Thank you.
Hello, my name is Michael and I'm going to be discussing some of the work that me and my lab mate Manas Mandel are doing at the Energy Systems Design Lab as part of the Utility Scale Energy Storage project in FES. So why does FES have a project that is dedicated to energy storage? Well, to lessen the impact of climate change, it is projected that a huge increase in renewables will be needed over the next 30 years, particularly wind and solar. But large-scale deployment of these renewables is complicated by the intermittency of wind and solar energy. For example, on the 13th of May in 2018 in California, there was a lot of solar energy generated around noon, but not enough demand, leading to about 12 gigawatt hours of energy being lost or curtailed. So we would like a way of storing that curtailed energy and using it at other times. There are a number of solutions, depending on the scale, some of which we study in our lab. However, me and Manas focus on hydrogen. So why hydrogen? Well, the main benefit is that it's very flexible. It can help to decarbonize many sectors. It can also be stored at large scales for months, and it's already a $120 billion commodity today with about 80 million tons being produced each year, which will have to increase significantly to help mitigate global warming. Currently, hydrogen is made by reforming natural gas, which is a pretty big carbon dioxide emitter. Ideally, we would like to use renewable energy to do water electrolysis, that is, the splitting of water into hydrogen and oxygen. Now, there's a few ways of doing this, each with their own pros and cons and readiness level. However, we will be focusing on PEM electrolysis, as this is the most popular technology, making up the majority of new electrolysis installations in recent years. It works by bringing water into the anode side of the electrolyzer cell. When it reaches the anode catalyst layer, a reaction occurs that splits the water into oxygen, protons, and electrons. The oxygen is typically vented, electrons travel through an external circuit to the other side of the cell, while the protons cross the polymer electrolyte membrane, aka the PEM, which separates the two sides and the hydrogen from the oxygen. The protons will recombine with the electrons to produce the hydrogen gas which we store. These devices are very expensive to make and run, however. We have to use iridium to split the water in the anode, as the conditions there are extremely harsh. And unfortunately, iridium is rarer and more expensive than platinum. The system is also quite inefficient. A lot of our energy from the renewables is wasted doing that water splitting in the anode catalyst layer. So people just tend to add a lot of iridium in there in the hope of getting good performance. So our work focuses on trying to better understand the anode catalyst layer and to try and reduce the amount of iridium that is needed. Manas did all the experimental work. The first step for him was developing a manufacturing process that gave good reproducible performance. The catalyst layer is only 4 microns thick, so it's made using an ink. Manas was the first to use inkjet printing to make them and was able to get a very good reproducible performance. Next, we wanted to characterize the anode catalyst layer so that we could use that information in numerical modeling. Manas was the first to measure the conductivity of the protonic phase and the electronic phase and show that the electronic conductivity is incredibly low and is much lower than the protonic. So the electronic conductivity is very low, but how do we know if this is important or not? Well, I do numerical modeling to find out. What we do is we take the part of the electrolyzer cell that we're interested in, which are the layers at the center of the cell, and we idealize this as a mesh. In each mesh element, we solve differential equations such as Ohm's law, which in this case will tell us what voltage the protons and the electrons are seeing, and this will depend on the conductivities that Manas measured. When we solve these equations, we get a map of what the voltages will look like. With this, we could do some post-processing to get a map of where that water splitting reaction is actually occurring. So we ran our model, and this is the polarization curve that we obtained, which is the main performance metric that is used. This curve shows the current on the x-axis. The higher the current, the more hydrogen we are producing. The y-axis is the voltage. The lower the voltage, the more efficiently our cell is running. But let's look at our map of the reaction in the anode catalyst layer when we are running at high currents and producing a lot of hydrogen. Yellow shows the high reaction rates, which is all at the left-hand side because of that very poor electronic conductivity. Most of the layer is actually purple, so it isn't actually catalyzing the reaction. It is actually just being wasted. So perhaps we can make a thinner layer which would reduce the amount of iridium catalyst that we use. Well, we simulated making the layer thinner and we actually got a slightly improved performance, but with 40 times less iridium than what we used to consider our standard. There is some experimental evidence for this in the literature for this performance increase with less iridium, and now our model can explain why this happens. So to conclude, hydrogen is going to be a big part of the climate solution, and we need to be making it renewably using water electrolysis. At the Energy Systems Design Lab, we have used both experimental and numerical methods to better understand what is happening inside the electrolyzer cell so that we can reduce the amount of iridium catalyst that is used. Thank you very much for listening.
In our research at the Alberta School of Business, we often adopt an organization theoretic perspective. In doing so, we aim to better understand social contexts and their implications on organization, management, and policy. My name is Bandita Deka Kalita, and today I'm sharing some interim findings from a process study with my supervisor, Joel Gaiman, on a transformation in the oil and gas sector of Alberta. The transformation we study is that of the organizing principles in the oil and gas sector. Also called institutional logics, these principles refer to the specific rules that inform that sector's practices, what actions they deem appropriate in that sector. For example, the appropriate practices in a family domain where the family logic prevails would differ from that in the market domain where the market logic prevails. We study how the logic of Alberta's oil and gas sector changed during the period between 1938 and 2019. Earlier, there was a focus on relentless profit-making, as exemplified by the image on your left of spectators watching oil explode from the Leduc No. 1 well in 1947. This extractive logic has undergone a sea change in more recent years. Companies are now more heavily scrutinized for their liability management efforts, as is indicated by the challenge of the orphan wells pictured to your right. To study how the logics transformed, we adopt a longitudinal and inductive research design. By longitudinal, I mean that our study covers an extended time period in which we observe regulatory practices during the respective tenures of 5 different regulatory agencies. By inductive, I mean drawing inferences from the data to build theory. Our data set consisted of interviews, archival documents, and observations. We analyzed these qualitative data using various methods, coding them into different categories such as time periods, meanings, organization types, etc. As we analyzed the data, we combined our emerging findings with theory from past work. The goal of this process is to develop new theory, that is, to move from specific observations in the data to broader generalizations about the phenomenon we study. So, what did we find? Well, we found that the process of logic transformation entailed 2 sub-processes. The first is a bottom-up process of evaluation, and the other was a top-down global institutional process. Let me briefly tell you about these processes. The bottom-up process of evaluation told us that logics transform as a result of a change in values. Discussions and debates around what constitutes or what counts as good and what organizational characteristics are worth holding in high regard showed us that people continuously reassess the question of worth or the question of what counts. We found multiple processes through which this collective assessment of worth took place across the decades. In the earlier extractive logic, these processes resulted in the prevalence of an indomitable spirit and a high regard for profit-making, whereas in the later period, this resulted in the prevalence of attributes such as accountability for your action and the inclusion of other stakeholders in consideration beyond simply profit-making. Top-down process of global institutionalization included the influence of cultural movements such as the environmental movement and other global events such as the Second World War and major economic downturns. For example, the problem of rampant bankruptcies arising from the oil price crash of 1980s led to companies leaving infrastructure on farmers' lands, and this put a spotlight on the cleanup issue. Apart from some key theoretical contributions to organization and management theory, we believe that by offering a processual understanding of change, our study can significantly help orient energy policy and organizational decisions in more effective directions. After all, any talk of future energy systems cannot be separated from the more substantive processes animating the societies these are intended to serve. Thank you very much.
Hello, my name is Moosa Moghimi, and I'm a postdoctoral fellow at the Sustainable Computing Research Group at the Computing Science Department of the University of Alberta. Today, I'm going to talk about our research on voltage regulation techniques in modern distribution systems. With growing concerns about global warming, we are seeing many new technologies being installed in the distribution systems, from smart meters and other measurement devices to renewable energy sources like rooftop photovoltaic installations, or to new electrical loads like electric vehicles, which all contribute to reducing fossil fuel consumption. To take advantage of all of these technologies and at the same time ensure safe and secure operation of the electrical grid, we need to have proper controls in place. And proper control starts with proper monitoring, which is why we started our research with studying different state estimation techniques that enable proper monitoring and control of the distribution systems. But there's more studies to do. With all the benefits that come with PVs and electrical vehicles come a lot of challenges. For example, consider an electrical distribution system that has many PV installations. Ideally, we want the voltage level to always stay within certain limits. That is safe for the consumers, the appliances, and for the grid equipment. But we see that around noon, we have some over voltages, which is caused by the extra PV generation. Also, we see some voltage violations in the evening, and the voltage goes below the allowed limit here due to the increase in the electrical load demand and the decrease in the PV generation. I should add that having additional electrical loads like electric vehicles make these matters worse. And I also should mention that traditional distribution systems have some methods to deal with these voltage violations, but they are not simply enough to address all of the problems introduced by this PV and EVs. But that's not all the problem. All of the EV owners typically want to charge up their vehicle right after they get home in the evening. So many of these vehicles demand charge power at the evening hours at the same time. And I should mention that a single electric vehicle can draw power equivalent to several homes. So it's easy to see that such high demand can cause overloadings for transformers and transmission lines, and eventually can damage equipment. To solve this problem, we rely on scheduling the electric vehicle chargings using reinforcement learning techniques. And we try to efficiently use the maximum capacity of the grid without causing any voltage violation problems or any overloadings. At the same time, ensure that the maximum possible power is delivered to the electric vehicles. To deal with the voltage rise problems in the distribution system caused by the PV installations, we rely on energy storage units or batteries. So the idea is pretty simple. We want to charge up the batteries around noon when we have extra solar generation available, and in the evening we can discharge these batteries and inject this extra power or extra stored energy back to the grid when the PV generation is at its minimum or is non-existent, but the load demand is at its peak. So in this way we can fix the discrepancy between the solar generation and the electrical demand. Sample results show that we can effectively regulate the voltage using these distributed batteries. And I should mention that we want to have a method that is distributed and preserves the privacy of the consumers and scales well for larger systems with many PV installations. Okay, that was my presentation. I hope it was informative, and I would be happy to take any questions. Thank you.
Hello everyone, my name is Bandita. I'm a graduate student from University of Alberta, and I'm working with a biofuel project team led by Professors Marty Luker and Venture. You may be wondering how a study of prices could possibly be interesting or relevant to you. In addition to being the amount that you have to pay, prices are important to the way that economies function. During the COVID-19 pandemic, demand for air travel and jet fuel dropped a lot, but diesel fuel trucks to deliver food remained important. Crude oil is currently a key input for making conventional jet fuel and diesel. Meanwhile, to reduce greenhouse gas emissions, new technologies are trying to substitute biomass for crude oil to make biojet and biodiesel. This analysis investigates current price relationships between crude oil, jet fuel, and diesel, and we could use this information to assist the development of the emerging biofuel industry. To investigate these price relationships, I estimate what's known as co-integration models to identify long-run price co-movements over decades for the short-run price adjustments within weeks. We employ nonlinear error correction models. Nonlinear models allow for different price responses in alternative states, rather than linear models, which only allow for a constant price response. As jet fuel and diesel industries have differential price responses to oil price increases versus decreases due to specific market structures, nonlinear models provide better insights. My analysis uses a US price dataset from 2000 to 2019, and this plot visualizes the three price series: diesel, jet fuel, and crude oil from top to bottom. Prices tend to fluctuate a lot and move up and down together over time, showing that jet fuel and diesel prices are affected by oil markets in the long term. Jet fuel and diesel prices are affected in the short term as well, but in different ways, depending on whether oil prices are relatively increasing or decreasing. For jet fuel, we can see two potential states in terms of price changes of crude oil relative to jet fuel. State 1 is when oil prices relatively increase, which leads to response 1 where jet fuel prices do not respond in the short run. State 2 is when oil prices relatively decrease and jet fuel prices do respond. Why is the difference? It could be due to pricing strategies of jet fuel producers to their price-sensitive consumers like airlines and their passengers. They could also use hedging strategies to manage unfavorable oil price changes. Diesel prices respond differently. In the short run, diesel prices only respond to oil price increases relative to diesel prices. You might have seen this in daily life. This is because diesel producers could exercise market power over dispersed consumers. Think about the COVID situation when public health has been seriously threatened. People considerably travel less, but still rely on diesel to deliver food. In a word, jet fuel consumption is relatively optional, while diesel is essential. My findings are important for producers and policymakers. Governments are considering what types of incentives jet fuel and diesel producers have for using bio feedstock to diversify fuel production away from fossil fuels. My results about jet fuel and diesel's vulnerability to oil prices show how important this diversification could be. It could improve the ability of emerging industries to mitigate price risks from crude oil shocks. Moreover, given that jet fuel prices are more vulnerable to oil price changes than diesel, biojet may be especially attractive to jet fuel producers. So, you see, understanding price relationships is important, not only because you and I have to pay these prices, but also because they are affecting the direction that the economy might go in response to climate change. Thank you.